Good evening. I welcome you all to the week 11 live interactive session for the course Polymers, Concepts, Properties, Uses and Sustainability. Now let's get on to the course. So as usual, uh, let's go through the brief recap of lectures of week 11. So lectures of week 11 included uh, lectures on polymer processing and recycling techniques. Lecture 78 was on rheology and entanglement. It was on concepts where uh, there was a discussion on rheometry, basically rheology, which is the study of deformation of fluids. And there was a discussion on shear and extensional flow. And then, on one-dimensional flow, which is, which occurs actually in a rheometer. And then the narrow gap and what are the controlled variables, what kind of tests that can be done in a rheometer, uh, and uh, and then the discussion was on rheometers geometry, especially the geometries used for rotational rheometers, where there was a discussion on cone plate rheometer, cone plate geometry, parallel plate and concentric cylinder geometry. Uh, the discussion was followed by a discussion on oscillatory shear response of polymer melt, where monodisperse polymer melt, especially monodisperse polystyrene response, uh, especially the storage modulus response with respect to shear rate was discussed. With respect to shear rate was discussed. Next, the extensional flow was discussed, where the extensional flow of different polymeric systems like LDP, polystyrene, especially the response based on branching were all discussed. The final discussion of the lecture was on fiber orientation in a shear and extensional flow. Lecture 79. Lecture 79 was an introduction to rheological models, where different class of models, the linear viscous models and the non-linear models, especially for the generalized Newtonian fluid, and then the linear viscoelastic model for a viscoelastic fluid were all discussed. This was followed by a detailed discussion on shear thinning models, especially the Carayo-Yasuda model and the Herschel-Buckley model. Then there was a discussion on the non-linear viscoelastic model, the Pantheon-Tanner model, where there was a discussion on what are the non-linear terms like multiplication of stress by stress or strain by strain or strain rate by strain rate. So these all gives non-linearity. And then what are the tensors used and what is the convected derivative. These were all discussed in detail, and how eliminating certain terms, and then the value of certain constants, if it is equal to 0, then you will end up with a linear viscoelastic model like your Maxwell model was discussed. The next discussion was on rheology and processing. It was based on uses, uh, and there was a detailed discussion on mixing in different flows, where the previous week's lectures it was discussed that in case of polymers the mixing is basically laminar, and how the extent of mixing varies when there is a simple shear flow and an extensional flow. For example, in case of simple shear flow, you have a linear material point separation, whereas in case of an extensional flow, you have a exponential material point separation. And there was a discussion on viscous dissipation, and this was followed by discussion on dye or extrudate swell, where the concept on stretching and orientation and recovery and entanglement and reptation, which leads to dye or extrudate swell, were discussed. And then what are the correlations with the rheological properties and influence of normal stresses were discussed. And then rheological properties and interfacial properties were also discussed. The role of rheological and interfacial properties were also discussed in case of dye swell. And this was followed by a discussion on deformation in a simple shear flow, where the velocity gradient, and strain rate tensors were discussed in detail. And what happens in case of a Newtonian fluid, or for non-linear, viscous or generalized Newtonian fluids were discussed. And then there was quite a bit of discussion on normal stress differences. And the final part of the lecture was discussion on different techniques of rheology, especially rotational, tube flows, extensional, and trade test in rheology. The next lecture was on absorption and leaching. So, what is the fate and transport of a polymer in environment? Being low low in density and non-biodegradable, it has a long life. So there will be a lot of interactions between small molecules and the polymer, and how the exchange happens. For example, small molecules can get into the polymer, which is called as absorption, and there is also a possibility that the molecules that got absorbed some time back, they may also come out of the polymer, or some are which are already there in the polymer. For example, plasticizer in a polymer can come out of the polymer, and this process is called leaching. What are the thermodynamics of solute exchange? So the solubility, concept of solubility, partitioning, and sorption isotherm, and how is the kinetics of solute exchange, all these affects the fate and transport of polymer in environment were discussed. And then the absorption kinetics, basically the Fickian, non-Fickian, and case 2 diffusion were discussed. And finally, the leaching and leaching kinetics were discussed. The next lecture was on swelling of polymers. So swelling of cross-linked polymers. So what happens, when there is a uptake of solvent in case of a uncross-linked, whether it is a linear or branched polymers. What happens in that case? So once the solvent starts entering, it plasticizes the polymer, then solubilization takes place, and then finally you form a polymer solution. Whereas in case of cross-linked polymer, due to the presence of cross-linking, the solvent cannot solubilize, but it plasticizes, and then it forms a swollen network. And then there was a discussion on the osmotic pressure and chain elasticity. So the balance between the two can determine the the swelling of the polymers. And what are the applications where the swelling of polymers are very useful, like in super absorbent material, for example in your diaper application, or sometimes it can be used in agricultural field also to impart moisture in the soil. And then how do you measure cross-link density? By developing correlation between the amount of swelling and the cross-link density. You could measure the cross-link density in a cross-link polymers, and then their applications in hydrogels and organogels were all discussed. This was followed by a discussion on Florigins theory and network elasticity, and then where the swelling ratio based on weight and volume were discussed. And then the next discussion was on network elasticity. The the osmotic pressure and the change in delta G with solvent was discussed. And the next was the network elasticity with the ideal chain and entropy based discussions were done. And finally, the Flory-Rayner equation was discussed in detail, and the kinetics of swelling, the mass transfer, large deformation, and relaxation. So all these three together in combination can play a very important role in kinetics of swelling of polymers. The final lecture of the week was on viscosity for polymer processing. Here in this lecture, the capillary rheometry was discussed in detail. So, what is the equation that can be used for a Newtonian fluid, where you use a Hagen-Poiseuille equation, and what happens in case of a viscoelastic fluid, and then what happens in case of a developing flow or an entrance effect. So where you use the end correction factors, a Bagley correction factor can be used. And finally, there was discussion on Maxwell model for viscosity, that is where you have a sinusoidal input of strain rate, and what is the model response for that was discussed in detail. And there was a discussion with an example uh, of the uh, Maxwell model response was also there. So now let's get on to the practice assignment session. First question. In a cone and plate viscometer, the rate of strain is related to speed of rotation of the cone, omega, the unit of which is radian per second, and the angle between the cone and the plate, alpha, the units of which is radians, by following relation. So, how is this rate of strain related to omega and alpha? Is a question. So, this is a GATE 2013 question. So, is it, the rate of strain, is it equal to omega into alpha? Or is it omega into cos alpha? Or is it alpha by omega? Or is it omega by alpha? So, how is this rate of strain or strain rate related? So, the solution is the rate of strain is related as omega by alpha. So, omega is the speed of rotation and we know the units is radians per second. And similarly, the angle between the cone and the plate is alpha. So, you can actually get the strain rate by dividing omega by alpha. So, from the units you can actually determine, because the unit of strain rate is second inverse. So, if, when you divide omega by alpha, and if you do the unit calculation, you will find out that omega is nothing but radians per second and alpha is radian. So, radian per second by radians. So, radian gets cancelled. So, you will get the unit as second inverse, which is nothing but your rate of strain. The next question. One of the key feature of rheometry is narrow or thin gap. So, why is it very important? And what does it make, what parameter does it make as insignificant when you have a narrow gap or a thin gap? So, narrow gap or thin gap makes the inertial forces insignificant. Next question. Perfect fiber orientation can be achieved in which type of flow? So, the perfect fiber orientation can be achieved in an extensional flow. When you have an extensional flow, the fiber orientation is much better. You will get, much more oriented fibers, in the direction of the extension. Next, for Newtonian fluids, extensional viscosity is related to shear viscosity as, what is the relationship between the extensional viscosity and shear viscosity in case of Newtonian fluids? So the answer is extensional viscosity, sorry, there is a typo error. Extensional viscosity is actually 3 times the shear viscosity. So, as we know that the behavior of the material, whether it is a Newtonian fluids or polymer, it may not be the same in a shear flow and an extensional flow. So, obviously, you will end up with a different viscosities. And in case of Newtonian fluids, you have a correlation that the extensional viscosity is 3 times the shear viscosity. Next, match the following rheometer geometries with the features or application. So, we have 3 geometries mentioned: cone and plate geometry, concentric cylinder geometry, and parallel plate geometry. And the features and or applications that are given here are low viscosity samples, non-uniform strain rates, uniform strain rates, suitable for paste-like systems. So, which of the geometry matches with which of the features or which of the application? The solution for this is a cone and plate geometry. It is related to uniform strain rates, because in a cone and plate geometry, if you see the cone and plate, so we know that the velocity increases radially. Okay, because your velocity is given by omega r. Okay, so where your omega is your rotational speed. Okay, so it is given so the velocity increases radially. Okay, the linear velocity increases radially. The angular velocity is given by omega, and the linear velocity is given by omega r. So so if it is, since it is omega r, the velocity, in the linear velocity will increase radially. So velocity at r equal to 0 will be 0, whereas velocity at r equal to r will be omega into capital R. So this shows that there will be a velocity increase in the radial direction. And similarly, since you have the top plate in the cone shape, you also have the gap which is increasing radially. So this compensates the changes in velocity, and thus you will end up with the uniform strain rates. Next, for concentric cylinders, these are very suitable for low viscosity sample, because here your torque is small as the area of contact between the solid and fluid is very large. Next, the parallel plate it can be used for paste-like system, and one of the features is that you will not have uniform strain rates. Why do you not have uniform strain rates? Is that, similarly, since it is, one of the plates is rotating, you will have angular velocity, and your linear velocity is a function of angular velocity into the radius. So obviously your velocity increases radially, whereas the gap is not increasing radially in case of a parallel plate. This means the velocity increase in the radial direction is not compensated by the gap increase. So you end up in a non-uniform strain rate. Because your velocity is given, your strain rate is given by your velocity by gap. So you will end up with, a non-uniform strain rates. However, due to the flexibility of the gaps in case of a parallel plate, because in case of a cone and plate, you will have very micro gaps, whereas in case of a parallel plate, you will have gaps in the range of 0.5 to 1 mm you can adjust. So it can be used for particulate or paste-like systems. Next, according to Carrier-Yasuda model, constant viscosity at lower shear rates is called. How do you define the constant viscosity at lower shear rates according to Carrier-Yasuda model? So Carrier-Yasuda model is a shear thinning model. So the constant viscosity at lower shear rate is called as zero shear viscosity. Next question. For a yield stress fluid having stresses up to yield stress, identify the type of flow for shear rate closer to zero. That is very low shear rates. So the stresses, you know, uh, are less than or equal to your yield stress, and the shear rates are also very low, which is very closer to zero. So what will be the type of flow for such a case in case of a yield stress fluid? Hope you can understand the question. So you have the shear rates of very low value, which is very close to a zero shear rate, and the stresses are also less than your yield stress. So what type of flow you can identify in case of a yield stress fluid? So the answer to this is that there will not be any flow for a yield stress fluid. For in case of a yield stress fluid, you have the Herschel-Buckley model, and from this model you can identify that your stress is equal to your yield stress plus K into shear rate to the power n. So when the values of stress, when the shear rates are very low and your stresses are up to your yield stress, I mean it is not at reached or it is not higher than your yield stress, there will not be any flow. So for a yield stress fluid, the stresses are to be higher than your yield stress. So it needs a particular yield stress to be crossed for it to flow. So until that kind of an yield stress is reached, there will not be any flow in case of a yield stress fluid, which is what is discussed in this question. Next, identify which type of flow, whether is it shear or extension, has a better mixing from the below figure. So you have a figure where you have a data which is given as you have a plot of specific energy versus area after deformation by area before deformation for a hypothetical sphere. So we have to identify for this from this which type of flow, whether it is a shear flow or extensional flow, there will be a better mixing. So you could see that here in case of a shear flow, the increase in specific energy is much higher for a particular area after deformation to area before deformation, whereas when you compare the extensional flow, this value is comparatively less. You could see that there's a continuous increase and the increase is very high in case of a simple shear flow, whereas in case of an extensional flow, the increase in specific energy is much lesser for the change in deformation. So from this we can identify that extensional flow has a better mixing as the energy required for mixing is low compared to that of a simple shear flow for a given deformation. Okay, given deformation in the sense if you consider 2 points, so upon applying a simple shear, the distance between the 2 points or the area change or the deformation change of a particular hypothetical sphere. So as you could see the sphere, imagine this is the area and this is the sphere. So when you apply a shear flow, the distance between the change in deformation will be much less compared to the change in deformation in case of an extensional flow. Or in other words, if for a particular set of particular deformation change, the energy required is much less in case of extensional flow, whereas it is much higher in case of a simple shear flow. So that means the points get separated so fast in case of an extensional flow that it gets mixed. Because if the distance between the 2 points or the the movement between the points is much slower, that means it is slowly mixing, so it is slowly moving past each other from one point to the other point, whereas in case of an extensional flow it is moving much faster. You can also see from this relation that in case of a simple shear flow, the material points separates linearly with time, whereas in case of an exponential flow, the material point separates exponentially with time. So if you integrate this equation, you will end up with a exponential equation. Next, according to general definition of normal stress difference for a viscoelastic fluid, N1 and N2 denotes normal stress differences in dash and dash. So the answer for this question is the normal stress difference N1 denotes the direction of flow, whereas the normal stress difference N2 denotes the direction of shear. So as you could find from this expression, so N1 is tau 11 minus tau 12, or that is equal to sigma 11 minus sigma 12. So this denotes, for example, you have two plates and the fluid flows in the x direction, whereas the shear changes in the y direction, the direction of shear, because one layer over the other it faces the shear. So this layer of fluid, this line of fluid will face shear. Similarly, it is like this, all these points face the shear in the vertical direction. Okay, the direction of shear is vertical, one above the other. So one layer of fluid will extend a shear over the adjacent layer. So the direction of shear is in the vertical direction, that is in the y direction. So that means your N1 is tau 11 minus tau 12, that is nothing but your tau xx minus tau yy, which is nothing but your direction of flow, whereas your N2 is tau 22 minus tau 33, which is nothing but equal to tau yy minus tau zz, which is nothing but your direction of shear. Next, the macromolecular scale reason behind development of normal stress difference in a viscoelastic fluid under shear is due to equilibrium dash like macromolecules or dash that leads to a tendency of dash. So what is the reason behind development of normal stresses in a viscoelastic fluid? This is what is the question. Okay. The answer is, so the equilibrium coil-like macromolecules are stretched where under the application of shear, and after it gets stretched, there is a tendency to recovery or recover back because of the inherent elastic nature of the material, and this is the reason behind normal stress differences. So it is not only in the shear direction there will be stresses, but the material starts, because of its inherent nature, to recover back after a stretched conformation. It has a nature to recover back, and this recovery causes a normal stress to develop, and that leads to a normal stress difference in the material under shear. Next, identify the techniques of rheology based on application of pressure from the below. So, extensional rheometer, U-tube viscometer, rotational rheometer, capillary rheometer. In which of these rheometers or viscometers there is application of pressure for flow of the fluid or flow of the polymer? So the answer is, in case of U-tube viscometer and capillary rheometer, in these two cases there is an application of pressure. So the pressure difference is what that leads to flow of the material through these two viscometer and rheometer. Viscometer and rheometer. Next, Identify the type of flow in rotational rheometers and capillary rheometers. What is the type of flow in rotational rheometer? The type of flow in a rotational rheometer is a cuvette flow. So in rotational rheometers you have two plates and one plate, two plates, or two concentric cylinders, or a cone and a plate. So as we have seen earlier, so in these conditions, one of the plates or one of these cylinders, it tends to move and the other is stationary. So the movement of the one of the plates causes the movement of the subsequent layers of the fluid. So this is based on cuvette flow. Whereas in case of capillary rheometer, as discussed in the previous question, so it is a pressure based rheometer where there is an application of pressure or there is a pressure difference which leads to flow. Next, identify the type of techniques of rheology for trade test from the below. So we have Abel-Hood viscometer, moving die rheometer, extensional rheometer, Monet viscometer, and Mel flow indexer. So in which of these are used as techniques of rheology for trade test? So the solution is moving die rheometer, Monet viscometer, and Melt flow indexer. These three are the uh, trade test based techniques of rheology or techniques of rheology for trade test. So moving die rheometer was discussed in week 10 lectures where there was a discussion on extent of cross linking in case of rubbers. So there along with it was also discussed along with the oscillating disc rheometer. So these two rheometers were discussed to determine the cure time. There was a discussion on induction, curing, and over cure and degradation, which is the data that can be obtained from a moving die rheometer or a oscillating disc viscometer. And similarly, Monet viscometer is also used for rubber viscosity measurements. And then melt flow indexer. This was also discussed in week 9 lecture, where a particular weight is placed in a piston die setup, where the weight is placed over the definite weight is placed over the piston, and then the polymer melt is passed through the die by through the piston. So how much is the flow of the polymer through the die? It determines the flow of the polymer, and based on the weights you can identify the melt flow index for the polymer. So these were discussed in the lecture 68. Melt flow indexer was discussed in lecture 68. So these are the three trade test rheology techniques that are used. Consider a polymer liquid system where the partition coefficient for a solute KPI is very much smaller than 1. Under this condition, dash process occurs. What is the process that occurs when the partition coefficient for a solute is KPI is very much smaller? So when KPI is very much smaller, okay, the process that occurs is leaching, because the affinity for the solute is more in the surrounding solvent or the surrounding medium compared to that of the polymer. So this leads to leaching of the solute from the polymeric system into the surrounding environment. So KPI is defined by concentration in polymer to the concentration in the surrounding medium, which is the solvent I. Okay, so here since the KPI is very small, that means the concentration in the solvent will be much more. So that means the partition coefficient is for the solvent is very small than 1. That means the material has much more affinity to the surrounding solvent. So the material starts leaching out of the uh, polymer. So the leaching process occurs. Next, uptake of a solute as a function of time in a polymer film sample is given by mt by m infinity. Mass uptake at time T by mass uptake, equilibrium mass uptake is equal to K absorption into T power n. The type of diffusion where absorption is a linear function of time is called. What is the type of diffusion when the absorption, that is mt by n infinity, is a linear function of time? So linear function of time means the power with respect to time is 1. That means n is equal to 1. That means this, in this case, you have case 2 diffusion. That means movement of front between glass and rubbery layer. That means what happens in this case of diffusion is that, so the material starts absorbing the solute particles, and it starts, and this layer, the initial front layer starts becoming rubbery, and then this layer starts, keep on increasing with time. So over the time, the extent of the glassy layer to the rubbery layer will become much more compared to the glassy layer, but it will be in, over the time. So it is a linear function of time. So it will be, first the frontmost layer which is exposed to solvent will become much more rubbery. Then the subsequent layer starts becoming rubbery upon uptake of the solvent. Next, identify the correct relationship for swelling ratio based on based on volume and polymer. Volume and polymer fraction. So swelling ratio based on polymer volume and the polymer volume fraction. So is it SV into 5P is equal to 1, or SV by 5P is equal to 1, or SV minus 5P is equal to 1, or SV plus 5P is equal to 1. Which of these relationship is correct for a swelling ratio based on volume and the polymer volume fraction? The correct answer is the swelling ratio based on volume multiplied by the polymer volume fraction 5P is equal to 1. That means your swelling ratio based on volume is inversely proportional to the polymer volume fraction. So as given here, so you have the volume of dry polymer, which can be written as 1 by 5P. So you have an inverse relationship between the swelling ratio based on volume and the polymer volume fraction. Next, in the context of polymer swelling, osmotic pressure can be estimated based on dash, while network elasticity can be estimated based on dash. How can you estimate osmotic pressure and how can you estimate network elasticity in the context of polymer swelling? So the polymer swelling, so under equilibrium there will be a the osmotic pressure will be equal to your network elasticity. So the balance between the two determines the polymer swelling. So if the osmotic pressure is more, then there's a tendency for the solute to enter into the polymer, whereas if the network elasticity is a counter effect that inhibits the solvent from entering into the polymer. So how do you estimate an osmotic pressure and a network elasticity in case of polymer swelling? So the answer for this is your osmotic pressure can be estimated based on change in Gibbs free energy of mixing with the number of moles of the solvent, and your network elasticity can be estimated based on ideal chain model, where the swelling leads to stretching of segments and a decrease in entropy. So from this decrease in entropy, you can find out the network elasticity. So this is how the relationship is given. So your osmotic pressure change is given in terms of your change in Gibbs free energy with respect to number of moles of solvent, and your network elasticity sigma, it is given by uh, the ideal chain model, where the swelling leads to stretching of segments and decreasing entropy. Since the segments are stretched, the number of possible conformation a polymer molecule can take decreases. When it is in a random coil state, it has much more entropy to change to different conformations, whereas when it gets stretched, then the possible conformation it can take up in a stretched condition will be much less. That means the number of conformation it takes is less, so that means there is a decrease in entropy. Okay. And this is what your Flory-Rayner equation is based on. So it is a equilibrium relationship between your osmotic pressure and your network elasticity. Next, identify if the statement is true or false. As the interaction parameter chi becomes more negative, the swelling ratio decreases. Is it true or is it false? So the answer is it is false. So when chi, your interaction parameter is more negative, the interactions are more favorable. So more and more chi being negative implies higher and higher is the swelling ratio. So you can identify from this relationship that, so as chi becomes more and more negative, so minus of minus becomes plus, right? So it, as it becomes more and more negative, the overall term it increases, whereas SV is your swelling ratio. So this term keeps on increasing as the chi becomes more and more negative. So minus of minus, so minus of minus 1 will be plus 1, whereas minus of minus 2 will be plus 2 here. So 2 so half plus 2 will be 2.5, whereas half plus 1 will be 1.5. So as this you can identify mathematically. So in physical significance, as you have more and more negative value of chi, that means there is more and more favorable interaction that between the solute molecule and the between the solvent and the polymer, and the solvent starts getting inside the polymer, and it starts swelling the polymer much more. Next, for a viscoelastic fluid, the relationship based on balance of linear momentum is used in capillary rheometry, where the relationship is given as, is it given as tau rz is equal to small r by capital R into tau r, or is it tau rz is equal to small r by capital R multiplied by tau r, or is it option C, tau rz is equal to r into delta p by 2l, or is it tau rz is equal to capital R by small r into tau r. So in case of a Newtonian fluid, you have a Hagen-Poiseuille relationship, whereas in case of non-Newtonian fluid, you do not have Hagen-Poiseuille relationship, but there is a, you can use a capillary rheometry based on the linear momentum balance. And how do you what is the relationship you can use for finding out the rheological behavior? So it is actually both option A and option C. So tau rz is nothing but your shear stress, and tau r is your wall shear stress, and small r and capital R are your uh, uh, radius at any point and your actual total radius or radius at the wall. Capital R is your radius at the wall. And similarly, option C is also right answer, where tau rz is equal to r into delta p by 2l. So how is it so? Let's see the relation. Actually, uh, for viscoelastic fluid, the overall stress in the material is a linear function of shear stress at the wall. So this defines the first option. So your overall stress is a linear function of shear stress at the wall. So tau rz, the overall stress tau rz is is equal to small r by capital R into tau r. Okay, and next, how do you define the relationship? So, if you look into the capillary rheometer, you may have a tube where there is a pressure-based flow. At the entry, you will have some pressure P1, which is a higher pressure compared to your pressure P2, and your pressure can be, changes in the flow direction. That is, it happens in the cross sectional area. So it is related to the cross sectional area. So your pressure force can be related as delta P into pi r square. Whereas your shear stress between the polymer and the wall, it happens at the in the area 2 pi rl. That is your curved surface area of the cylinder. Okay, so it is 2 pi rl into tau r. So if you equate both these based on the linear momentum balance equation, you will end up with your shear stress at the wall is equal to capital R by 2 into delta P by L. So if you just substitute, the value of tau R in terms of delta P in the relation of your overall stress to your wall stress, you will end up with the relation that, so you will have small r by capital R into tau R. So small r by capital R into capital R by 2 into delta P by L. So your capital R gets cancelled. So you will end up with small r into delta P by 2L. So that is why your shear stress is equal to R into delta P by 2L is valid. Next. According to the solution of Maxwell model based on viscosity for an oscillatory strain rate, the first term corresponds to what? What does the first term corresponds to? First term of viscosity corresponds to oscillatory strain rate. That is nothing but your complex viscosity. The first term of complex viscosity, that is your real part. That is eta prime corresponds to what? So actually it corresponds to viscous contribution to the stress as it is in phase with the strain rate. So when the stress is in phase with the strain rate, then your viscosity eta prime corresponds to your viscous contribution to the stress, whereas your eta double prime corresponds to your elastic contribution. So this is what is the relationship. So this is the solution for a Maxwell model, and your in phase it corresponds to the viscous contribution to the stress, whereas your second term corresponds to your cos omega t term corresponds to your elastic contribution, which is nothing but your viscous contribution is eta prime, whereas your elastic contribution is your eta double prime. Next, Cox-Meier's rule relates complex viscosity to complex modulus in polymers. Is this statement true or false? Does Cox-Meier's rule relates complex viscosity to complex modulus in polymers? The statement is actually false. Cox-Meier's rule predicts complex viscosity and steady shear viscosity are equivalent when angular frequency is equal to the steady shear rate. So as you can observe from this plot, so when the material obeys Cox-Meier's rule, your complex viscosity and your there is the real part of your complex viscosity, that your eta prime, the viscous contribution of the complex viscosity eta prime, and your steady shear viscosity eta superimpose on each other, under the condition that when angular frequency is equal to your steady shear rate. And this applies mostly for simple systems like polymer melts, whereas Cox's rule is not obeyed when the system is much more complicated, like you have some fillers, or if you have some structural complications like liquid crystalline portions, or in case of your gels or cross-link system, the Cox's rule is not obeyed. So for only for a simple system, this Cox's rule is obeyed, where your complex viscosity and your steady shear viscosity superimposed on each other under the condition of same angular frequency and steady shear rate. Next, let me also discuss some of the questions posted in the forum in the last session, that is July-November 2022 session. So this was posted by one of the students called Uday Kumar, and he had asked a question: mixing of polymer with another polymer is called polymer blend, whereas mixing of individual materials is called composite. So such a way that can we call all polymer blend as a composite? So this was his question. He is asking whether we can call polymer blend also as composite. So this was the reply given by the Professor Abhijit Deshpande, who takes this course. So he has mentioned that polymer blends is mixing of two different polymers. Even under polymer blends mixing of even under polymer blends. So even in the case of polymer blends, when you mix two immiscible polymers using a compatibilizers, it is classified separately and it is not called as a polymer blend, but it is called as a polymer alloy. So generally, when you mix two polymers, you call it as a polymer blend. But even in that case, when the polymers are immiscible, and you actually mix them using a compatibilizer, then that system is called as polymer alloys. So polymer composite is much different. Here you mix a polymer with a completely different class of material, like you mix it with a glass fiber, or you can mix it with a carbon nanotube. Okay, so the class of material itself is different. It is not the polymer with which it is mixed in case of polymer composite. It is polymer is mixed with some other material like your glass fibers or your jute fibers or your carbon nanotubes, etc. So in that case, it is called as a polymer composite, and ideally we should not, avoid confusing between different systems. Okay, so all these three are very different systems and they have their own names, and it is not advisable to confuse name between these systems. Next, uh, there was also a question actually, what is happening in the particular video. This was also asked in July-November session. I think the pictures were not there in the video, whereas you could actually observe those images in the downloaded lecture. So they've asked, you know, uh, especially on the movement of two particles. So in shear flow, you have the flow and the particle moves in this direction, these two direction, and the flow is actually makes the particle separates linearly with time. Whereas in extensional flow, the particle movement will be in this direction and it will be an exponential separation between the particles. So this figure was not observed in the video, whereas this is found in the lecture when you download the lecture, actually when you download the PDF of the lecture. So these were some of the questions that were posted in the forum in July-November 2022 session, that is last year's session. So thank you. That's it with the session. And have a nice evening. Thank you all. And that's it with the session.